just doing this very quick chapter wrapper that includes this quantum number wrapper as well as an equation wrapper. I did want to go back though. I just realized I was confusing myself with a letter that I was using, and I wanted to make sure that that's clear. Yes, so right here where I was calling the z component jz equals mlh bar, that's correct. Here I got to get rid of that z, all right? So it's just J, the total magnitude, okay? And of course, I got to get rid of this Z right here, right? So that was just L squared total magnitude and just J. Because again, those are the total magnitudes. So hopefully that clears up a bit of confusion for you. And so let's talk about these quantum numbers, okay? And so of course, what's not on here is our principal quantum number N. But we're going to actually see in the next chapter how N connects to all of these quantum numbers. Okay, so let's first start with orbital angular momentum quantum number L. Takes on values 0, 1, 2, etc. Okay, and so the specifics about L, so what's important to remember is L gives us the total magnitude of angular momentum, and that's given by root L times L plus 1 h bar, okay? So we have our magnetic quantum number, ML, which takes on values L, L minus 1, all the way down to minus L, which means, of course, there are 2 L plus 1 values of ML. So once again, if L is equal to 0, 2 times 0 plus 1 is 1, so that means there's only one ML value for L equals 0. If L is equal to 1, then 2 times 1 is 2 plus 1 is 3. So that means there would be 3 ML values, and they are -1, 0, and +1. Okay? And the thing to remember about ML is it gives us the component of angular momentum specifically on the z-axis. Okay? So Jz is given by mlh bar, and I'll just use the letter J. So for just total angular momentum, J, right, is given by root L plus 1 h bar, okay? So what about spin? So S is technically the spin quantum number, and for electrons, that number is 1/2. Okay. As we go a little bit further down the rabbit hole, we'll talk about spin quantum numbers for photons, but that's all that we're going to do in this class. You know, we're not really going to get heavy into the particle physics stuff. Okay. And so just like was given by L, S is the total magnitude, which takes on root S times S plus 1 h bar. Okay. And MS, you know, this is showing it takes on values plus minus 1/2, but MS is technically S minus 1, all the way down to minus S. So ML and MS are like twins, okay? And so also, right, the MS gives us the component on the z-axis of angular momentum, MSH bar, okay? So now, I didn't talk about this in the previous lectures, but we have the total. And I kind of alluded this a little bit with this picture that I drew right here, right? So here we have, I'll give this as, let's see here, to use the right numbers. Yes, so I'll give this one as, you know, ML. This one is given as MS, okay? And I'm just talking about the Z components there, right? But both of those angular momentums are going to couple to give us total angular momentum. And that's represented by lowercase j for the quantum number, okay? And what's going to end up happening, because L and ML show the same dependency as S and MS, J, the total, is going to do the same thing. For one, we notice that its magnitude is given by J times J plus 1, all square root, okay? But this quantum number J, which we haven't seen up until now, is actually the sum of the orbital angular momentum quantum number and the spin quantum number. So in other words, it's L plus S. And so it can take on values L plus S minus 1, all the way down to L minus S. And fortunately for us, because electrons only have one quantum number possible, which is 1/2, then when we start putting this quantum number J together, which we're going to start doing once we really get into spectroscopy, we don't really see this quantum number J until, we get into the spectras. For us, luckily, that's going to be very easy. And so it's always going to be just L plus 1/2. L plus 1/2 minus 1, all the way down to L minus 1/2. Okay? And so just like the other pairs of quantum numbers, the total magnetic quantum number is given by mj. That's given as the component on the z-axis, mj h bar. And of course, just like ml goes from L to L minus 1 all the way to minus L with 2L plus 1 values, right? ms technically does the same thing. It goes from S to S minus 1 all the way to minus S. And just to demonstrate that, right, ms has 2s plus 1 values. And so because s is only equal to 1/2 for electrons, right, we get 2 times 1/2 plus 1 equals 2 values. And of course, those values are plus or minus 1/2, okay? And so then we would see the same thing for mj. mj will take on 2j plus 1 total degenerate values, okay? So we're going to see the use of all of these quantum numbers quite heavily in spectroscopy. So make sure that you're familiar with these, okay? And then we're also going to see how principal quantum number n connects to all of these. Okay, so let's do an equation wrapper. So this is at the end of the book, and I find this quite useful because we came up with a lot of equations, a lot of different models, translations, vibrations, rotations, and we saw a lot of consistencies with each of those models, okay? So let's talk about them briefly. So the wave function of a free particle in one dimension, this is our classic wave function that we've been seeing over and over again, okay? And so the energies of this free particle are given by k squared h bar squared over 2m, where here this k squared is our wave number from this wave function, okay? And when we turn this free particle into a particle in a box, right? So free particle means that it's just able to float around wherever it wants. It has no potential energy barriers. But our particle in a box, right, it does have a potential energy barrier, okay? And from that model, that's where we got principal quantum number. Okay, I'll just write it as principal, okay? And of course, we could expand, and so there's the energy solutions for that particle in a box. And of course, we did that with 2 dimensions, right? And we could see that it still worked out very similarly as did the 1-dimensional particle in a box model, okay? So we have the wave functions of the harmonic oscillator model and the energies of the harmonic oscillator model, okay? And as it turns out, this harmonic oscillator model is not going to be so useful for us when we talk about the hydrogen atom, which is coming up next. However, when we get into talking about molecules, right, that have a bond with 2 different nuclei that are free to vibrate, this harmonic oscillator model becomes incredibly useful when discussing spectroscopy and simple linear molecules, okay? So we're not really going to see much of this vibrational harmonic oscillator model in the next chapter, but we will see it again when we get back into spectroscopy. What we are going to see quite heavily in the next coming chapter when we try to describe the hydrogen atom, and that's our goal. So our goal is we're going to take a proton and put it in some center of an origin, right, of an XYZ coordinate system. And we're going to allow an electron. Oops, I wrote theta, but I meant to write E minus. And we're going to put this electron in an orbit around this proton. That's how we're going to build up our model of the hydrogen atom. So as it turns out now, all of these things we've talked about on rotations, particularly the quantum numbers, as well as all of this angular momentum stuff, that's going to be really, really important for building up our hydrogen atom model. Okay? So wave function for a particle on a ring and the energies, angular momentums, particle on a sphere, and so forth. Okay? So this is a good set of review equations for a quiz or for like the midterm super quiz that's going to come up, right? This would be good stuff to study just as far as knowing the equations and knowing what they give us, what the important things are. Okay, folks, so I just wanted to record that very brief wrapper for this chapter 8. Coming up is chapter 9. And again, in chapter 9, we are going to take everything we've learned so far and try to describe the actual hydrogen atom using Schrodinger equation, as well as all of this other stuff. It's going to be very cool and exciting. Okay, I'll see you later.